What lies beyond the edge of our solar system? Decades ago, this was a question no one could answer. That is, until NASA's Voyager spacecraft set out on their groundbreaking journeys. Voyager 1 and 2 have been traveling for over 45 years, carrying humanity's curiosity beyond what we ever imagined. What they've discovered at the edge of the solar system has not only stunned scientists, but also redefined our understanding of space. Join us as we dive into the mind-blowing revelations these tiny spacecraft have uncovered in interstellar space. The Voyager mission was launched in 1977 with the ambitious goal of exploring the outer planets. Voyager 1 and Voyager 2 were equipped with cutting-edge technology for their time, designed to study Jupiter, Saturn, Uranus, and Neptune. After completing their primary mission, both spacecraft continued their journey toward the edge of our solar system. What sets Voyager apart is their longevity and the fascinating data they've transmitted back to Earth. These spacecraft have traveled over 14 billion miles from the Sun and are now in interstellar space. They've provided humanity with unprecedented insights into the mysteries of the cosmos, revealing data that scientists are still analyzing today. But their most shocking discoveries came as they crossed into uncharted territory, the heliopause. The heliopause is the boundary where the solar wind from our Sun meets the interstellar medium, the vast expanse of material between stars. Voyager 1 crossed this boundary in 2012, followed by Voyager 2 in 2018. What's surprising is the dramatic change in the environment they detected. As they entered interstellar space, the density of particles increased, contrary to what scientists initially expected. This discovery suggested that interstellar space is far more active and dynamic than we had assumed. Furthermore, Voyager's instruments recorded a sudden drop in solar particles and a rise in cosmic rays from outside the solar system. This shift marked the spacecraft's official entry into a realm beyond the Sun's influence, a milestone in human exploration. One of the most intriguing discoveries made by Voyager is the detection of plasma waves in interstellar space. These waves are created when cosmic rays interact with the particles in the interstellar medium. Using its plasma wave instruments, Voyager recorded eerie, low-frequency hums that give scientists crucial insights into the density and composition of interstellar plasma. These findings shocked NASA because they contradicted long-standing theories. Instead of a silent void, interstellar space appears to be teeming with activity. The plasma waves also provide a way to map this otherwise invisible environment, offering clues about how stars and galaxies interact on a universal scale. Voyager also uncovered surprising details about cosmic rays' high-energy particles that travel through space at nearly the speed of light. As the spacecraft ventured beyond the heliopause, they detected an increase in these particles, suggesting that the heliosphere acts as a shield, protecting our solar system from some of these energetic particles. Additionally, Voyager has revealed unexpected twists in the interstellar magnetic fields. The data suggests that these magnetic fields are not uniform, but instead exhibit turbulence and fluctuations. This revelation challenges previous models of how magnetic fields behave on cosmic scales and hints at the complex dynamics shaping our galaxy. The discoveries made by the Voyager spacecraft have revolutionized our understanding of space. They've shown us that the edge of the solar system isn't a static boundary, but a dynamic and ever-changing frontier. From plasma waves to cosmic rays, the data Voyager has collected continues to challenge and refine our scientific models. The mission also underscores humanity's ability to reach for the stars literally. With only a small amount of power remaining, the Voyager spacecraft continue to transmit valuable data, inspiring future generations of explorers. Their journey serves as a reminder of how curiosity and innovation can push the boundaries of what we know. When Voyager crossed the heliopause, scientists anticipated turbulence as the solar wind met interstellar space. However, the data revealed an eerie calm. Unlike the chaotic environment within the heliosphere, interstellar space appeared quieter, with particles moving more predictably. This surprising discovery challenged our understanding of how solar wind interacts with the surrounding galactic environment. The silence raised new questions about the mechanics of particle movement beyond our sun's influence. What forces shape this calm, and how does it vary across different parts of the galaxy? Beyond their scientific instruments, Voyager 1 and 2 carry something truly unique, a golden record. This 12-inch gold-plated copper disc contains sounds, music, and images that represent the diversity of life on Earth. It's humanity's time capsule for any extraterrestrial beings who might encounter it. The golden record reminds us that Voyager is more than a mission of discovery. It's also a symbol of hope, unity, and curiosity. The inclusion of greetings in 55 languages and natural sounds, like wind and waves, demonstrates our collective desire to reach out and connect with the cosmos. One of the most remarkable feats of the Voyager mission is its longevity. Both spacecraft rely on radioisotope thermoelectric generators, RCHEs, for power, which convert the heat from decaying plutonium-238 into electricity. Despite their incredible distance from Earth, Voyager continues to operate on less than 300 watts of power, less than a standard household light bulb. NASA has carefully managed power consumption by turning off non-essential systems, allowing the spacecraft to continue transmitting valuable data even as their power diminishes. The interstellar medium, the vast space between stars, was once thought to be empty. However, Voyager's data proved otherwise. This region is filled with gas, dust, and charged particles that influence the formation and evolution of stars and planets. Voyager's instruments have helped scientists understand how the interstellar medium interacts with the heliosphere and how these processes shape our galaxy. By measuring the density and temperature of this environment, the mission has opened new doors for studying the life cycles of stars. As Voyager ventured farther into interstellar space, it detected faint shock waves caused by ancient supernovae. These waves provide clues about stellar explosions that occurred millions of years ago and their impact on surrounding space. Understanding these shock waves helps scientists trace the history of our galaxy and the forces that have shaped it. Voyager has yet to reach the Oort cloud, a theoretical shell of icy objects surrounding our solar system. Estimated to begin around 2,000 astronomical units from the Sun, this region remains one of the least understood parts of our solar neighborhood. Although Voyager won't survive long enough to explore the Oort cloud, its journey has set the stage for future missions. By mapping the solar system's boundaries, Voyager has provided crucial insights into where the Oort cloud begins and how it interacts with interstellar space. Interstellar dust grains, detected by Voyager, are more than just tiny particles floating through space. They're essential building blocks for stars and planets. By analyzing the composition of this dust, Voyager has revealed its origins, which range from distant supernovae to the remnants of dying stars. These discoveries highlight the interconnectedness of the universe. The same materials that formed Earth and its inhabitants can be found drifting through interstellar space, waiting to spark new cosmic formations. Another fascinating finding from Voyager is its data on the magnetic bubble surrounding our solar system. Known as the heliosphere, this bubble shields us from a significant portion of harmful cosmic radiation. Voyager's journey beyond this boundary has shown how the heliosphere interacts with the galactic magnetic field. The spacecraft's findings suggest that the heliosphere is shaped not only by the Sun, but also by forces from the galaxy itself, leading to a deeper understanding of cosmic interactions. One of the emotional aspects of Voyager's mission is its isolation. Traveling billions of miles away from Earth, Voyager exists in a realm devoid of the familiar solar influence. This solitude is both humbling and inspiring. It reminds us of the vastness of space and our ability to send a piece of ourselves into the unknown, enduring against all odds. Voyager's crossing of the termination shock a boundary where solar wind slows dramatically occurred earlier than scientists predicted. This unexpected finding suggested that the heliosphere is more compressed in certain areas due to external forces, such as the interstellar medium's pressure. These insights have reshaped how we model the boundaries of our solar system, highlighting the dynamic nature of this region. Voyager discovered streams of particles moving in specific directions in interstellar space, referred to as interstellar winds. These winds are created by the movement of the interstellar medium and influenced by nearby stellar activity. This discovery provides clues about how interstellar material flows through the galaxy and interacts with objects like the heliosphere. By analyzing these winds, scientists can better understand the larger structures and dynamics of our galaxy, including how material circulates between stars. Cosmic radiation is one of the most significant hazards for deep space exploration, and Voyager has been instrumental in studying its intensity and composition. Once beyond the heliosphere, Voyager recorded an increase in galactic cosmic rays, high-energy particles originating from supernovae and other distant events. This data is critical for planning future human missions to deep space, as it helps researchers understand the radiation environment astronauts would face. Voyager's findings are paving the way for innovations in spacecraft shielding and mission design. Although not designed to search for life, Voyager has contributed to astrobiology by studying the environments of the outer planets and their moons. Data from the spacecraft revealed active volcanism on Jupiter's moon, Io, and the potential for subsurface oceans on Europa. These findings fueled interest in the habitability of icy moons and informed the design of missions like Europa Clipper, which will further investigate these worlds for signs of life. Voyager's role in identifying these targets highlights its enduring legacy in astrobiological research. Voyager's precise measurements of signals transmitted back to Earth have allowed scientists to test aspects of Einstein's theory of general relativity. As the spacecraft's radio waves travel vast distances, they experience gravitational effects that align with Einstein's predictions. This real-world testing of fundamental physics underscores Voyager's versatility as a scientific tool. Even decades after launch, the spacecraft continues to provide valuable data for theoretical and applied physics. Voyager's groundbreaking journey has directly inspired a new generation of space exploration missions. Concepts like the Interstellar Probe, a proposed mission to go even farther than Voyager, are rooted in the lessons learned from this iconic program. Additionally, Voyager's discoveries have motivated the search for exoplanets, interstellar exploration, and the development of advanced propulsion systems. Its success proves that even modestly equipped spacecraft can achieve extraordinary feats, encouraging scientists and engineers to think big and dream even bigger. The heliosheath, the outermost layer of the heliosphere, is a turbulent region where the solar wind slows and interacts with interstellar material. Voyager provided unprecedented data on the structure of this region, revealing complex patterns of magnetic fields and particle flows. These findings are critical for understanding how our solar system interacts with the galaxy. They also help scientists model how similar boundaries might exist around other star systems, broadening our perspective on stellar environments. One of the unsung achievements of the Voyager mission is its contributions to space communication. As the farthest human-made objects from Earth, Voyager's signals take over 20 hours to reach us, traveling at the speed of light. NASA's Deep Space Network has been essential for maintaining contact, and the mission has driven innovations in communication technology. The ability to transmit and receive faint signals across billions of miles has set the stage for future interstellar missions. Voyager's journey has provided a template for understanding other solar systems. By studying the boundaries of our own heliosphere, scientists can infer the structure of stellar bubbles around other stars. This comparative approach enhances our knowledge of how solar systems form and evolve. It also aids the search for habitable exoplanets by helping us understand the conditions necessary for shielding planetary systems from cosmic radiation. Voyager's incredible lifespan has taught NASA invaluable lessons about designing long-term space missions. The spacecraft's ability to operate for over 4 decades, despite harsh conditions and limited resources, is a testament to robust engineering. These lessons are being applied to new missions, ensuring that future spacecraft can survive for extended durations and continue to operate far beyond their original goals. Beyond its scientific achievements, Voyager represents the human spirit of exploration. Its journey into interstellar space is a powerful symbol of humanity's desire to understand the universe and our place in it. The mission reminds us that exploration is as much about asking profound questions as it is about finding answers. Voyager's enduring legacy will inspire generations to continue seeking knowledge, no matter how distant the horizon. Voyager has provided invaluable data on how solar storms interact with the heliosphere. These intense bursts of solar energy can travel across vast distances, impacting not only Earth, but also the outer reaches of the solar system. As Voyager traveled beyond the heliosphere, it detected traces of past solar storms, showing how these phenomena propagate through space. This data helps scientists model the potential effects of solar storms on other planets and spacecraft, which is critical for planning missions to the outer planets and beyond. Voyager's instruments detected anisotropies, or directional variations, in cosmic ray intensity. These variations suggest that cosmic rays are not evenly distributed in interstellar space, likely influenced by magnetic fields and nearby stellar phenomena. Understanding these patterns has helped scientists refine their models of the interstellar medium and the forces shaping it. It also provides insights into the origins of cosmic rays and their journey through the galaxy. Voyager's trajectory has offered opportunities to study how the spacecraft interacts with gravitational forces from the Sun and other celestial bodies. As it moves farther into interstellar space, these interactions become subtler, but they still influence its path. This data provides a unique testbed for understanding gravity's effects over vast distances, contributing to the study of orbital mechanics and the long-term dynamics of objects leaving the solar system. Voyager's legacy extends beyond science into popular culture. From Carl Sagan's famous reflection on the pale blue dot to its appearances in films, books, and music, Voyager has become a symbol of humanity's curiosity and ingenuity. The Golden Record, in particular, captures the imagination of millions, representing a message in a bottle sent into the cosmic ocean. Voyager's cultural impact ensures its story will be told for generations, inspiring creativity and exploration in all forms. Space weather, caused by solar activity, has a profound effect on the heliosphere. Voyager has shown how these changes ripple through the outer reaches of the solar system, altering the heliosphere's size and shape. By studying these effects, scientists gain a better understanding of how the Sun influences not only Earth, but also the broader interstellar environment. This knowledge is crucial for developing technologies that can withstand the impacts of space weather. The Voyager mission highlights the technical challenges of interstellar travel, from energy constraints to communication delays. Its success has informed the design of future spacecraft, including advanced propulsion systems like solar sails and nuclear propulsion. The data Voyager has collected about the conditions in interstellar space is invaluable for designing missions that aim to go even farther, such as probes to nearby star systems. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity